Testing, can you hear me? Testing, can you hear me? Alright, this video is public now. Um, Hold on. Alright, so last stream I was studying about second order linear equation. I was studying about second order differential equations. I studied about linear equations and they said that the solution was they gave a summary of solution. Yeah. So they said they said solution was something like e to the power of lambda x, and then lambda could take any of these values. Uh, yeah, lambda can be either this, or this. Basically, what they said was if you have an equation like this, then the solution would be e to the power of lambda x. You can take lambda x out, then we are left with this, but this would be equal to 0 because this can't be 0. Since this entire equation is 0, this is all of this is 0. But since all of this is 0, lambda e to the power of lambda x cannot be 0. This a lambda square plus b lambda plus c, this has to be 0, right? So that's how they got this. And if lambda has, there are three cases. If lambda has distinct roots, lambda has a single root, lambda is a complex conjugate, then the final solution could be any of these three. This case over here is where is it? Homogeneous linear equation. Wait. Uh, so if this over here is 0, so we have something multiplied by double derivative of y plus something multiplied by derivative of y plus something multiplied by y is equal to something, then it's not homogeneous. But if this r over here is 0, then it's homogeneous. So far we have dealt with homogeneous so far we have dealt with linear homogeneous equations, and the next chapter is about non-homogeneous linear equations. Uh, did they say, hold on, homogeneous, non-homogeneous? Where is the definition of linear? Oh, yeah. Linear as in double derivative, then derivative, and then y, and then it's just these three, and maybe a constant over here. But if it's some coefficient multiplied by this, some coefficient multiplied by this, plus some coefficient multiplied by this, and is equal to 0. But what's not linear is this y square over here. This is not non-linear. Yeah, non-linear because of the y square term. Anyways, Going to the next chapter. General solution to a non-homogeneous linear equation. Consider the non-homogeneous linear differential equation. This the associated homogeneous equation is this is called the complementary equation. We will see that solving the complementary equation is an important step in solving a non-homogeneous differential equation. A solution yp is of a differential equation that contains no arbitrary constant is called a particular solution to the equation. Let yp be any particular solution to the non-homogeneous linear differential equation. Also, let C1 y1 and C2 y2 denote the general solution to the complementary equation. Then the general solution to the non-homogeneous equation is given by C1 y1 plus C2 y2 plus yp. So the proof is we have this. We can take a 2 out. Double derivative. Wait, what are they doing here? To prove why x is the general solution, we must first show that it solves the differential equation. Okay, so they plugged this in. So the double derivative of y, oops, double derivative of y plus single derivative of y plus y itself. And solving this, we are left with 0 plus rx. We are left with rx, which is the what it's supposed to be. Now let Cx be any solution to this. Then z minus p yp plus this is equal to this. But since z and yp are solutions, we end up with rx which is equal to 0. C1 y1 plus C2 y2 is a general solution to the complementary equation. So there are constants C1 and C2 such that we have this. Hence we see that Cx is equal to C1 y1 plus C2 y2 plus yp. The method of undetermined coefficients involves making educated guesses about the form of the particular solution based on the form of Rx. When we take derivatives of polynomials, exponential functions, sines, and cosines, we get polynomials, exponential functions, sines, and cosines. So when Rx has one of these forms, it is possible that the solution to the non-homogeneous differential equation might take that same form. Let's look at some example to see how this works. Undetermined coefficient when Rx is a polynomial. Complementary equation is this, with general solution c1 e to the power of minus x plus c2 e to the power of minus 3x. Since Rx is 3x, particular solution might have the form ax plus b. If this is the case, then we have derivative is a, the double derivative is 0. For yp to be a solution to the differential equation, we must find values for a and b, such that this is equal to 3x. This is equal to 3x. And then we end up with this. Then a is equal to, okay, from these two, get a is equal to 1 and b is equal to minus 4 over 3. And then we have this. Notice that even though Rx did not include a constant term, it was necessary for us to include the constant term in our guess. If we had assumed a solution of the form yp is equal to ax, we would not have been able to find a solution. If the function Rx is a polynomial, our guess for a particular solution should be a polynomial of the same degree, and it must include all lower order terms regardless of whether they are present in Rx. Find determinant coefficients when Rx is an exponential. Find the general solution to double derivative of y minus derivative y minus 2y is equal to 2e3x. Let's wait. I forgot to open my Excalibur. All right. So this is equation 7.13. Sorry, example 7.13. Is it? Yeah, yeah. And they're asking double derivative of y minus derivative of y minus 2y equals e to the power of 3x, right? 2 times e to the power of 3x, right? Now, if the equation was if this was the equation, then the general solution would be 1 lambda square minus lambda minus 2 lambda, sorry, just minus 2 is equal to 0 minus p plus minus p square minus 4 times a times c plus 8. So this is 9 over 2. 9, this becomes 3. So 1 minus 3 and 1 plus 3. 1 minus 3 is negative 2. 1 plus 3 is 4. So we are left with 2. So the solution is y. This looks like a g. Y is equal to c1 e to the power of minus x plus c2 e to the power of 2x. Then we need to find a particular solution. I'm still confused on how to find a particular solution. The particular solution might have the form ax plus b. Involves making educated guesses when we take derivatives of polynomials, exponential functions, sines, and cosines. We get polynomials, exponential functions, sines, and cosines. So are they saying that VP, are they saying that there's a particular solution which is of the form a to the power of b x, a to the power of bx? Now, let's say this is okay, never mind. Particular solution, let's do the double derivative. Actually, let's do a single derivative. Single derivative is a b b x, and then particular solution a b square e to the power of b x. We must find values of for a and b such that how did they get these three? Oh, I see. I see. They put this here. So then, uh, putting this here, we have ab square e to the power of bx, right? Minus ab minus 2 times a. This is equal to 2 times e to the power of 3x. And then what? A and e to the power of bx repeats all of these. A e to the power of bx repeats in all of this. We have a b square minus b minus 2 is equal to 2 times e3x, right? B square repeats. If b was 3, 3 square is 9. Minus 3 minus 2. Let b equal 3. A to the power of 3x. 9 minus 3 minus 2. 9 minus 5. So minus 4. This implies that A is equal to negative half. So then we have C1 to the power of negative x, and then the next one is 2x. Minus this is the general solution. I don't like this educated guess thing. Why did they say plus? Hold on. Why are they saying plus? Minus 2y minus 2y minus 2y. Oh, wait. This is positive 4 plus half. I don't like this educated guess thing. Initial guess for yp. So constant ax plus b quadratic. Same way, this. Okay. Keep in mind that there are key pitfalls to this method. Consider the differential equation of y double derivative plus 5 derivative of y plus 6y is equal to 3x to the power of minus 2x. Based on the form of Rx, we guess a particular solution of the form a times e to the power of minus 2x. Shouldn't it be e to the power of bx? Oh, so the lambda doesn't change. But when we substitute this expression into the differential equation, we find that differential equation to find the a value for a, we run into a problem. We have this, this, and then we end this with 0, which is not possible. Look closely, we see that in this case, the general solution to the complementary equation is this. Exponential function in Rx is actually a solution to the complementary solution. So as we just saw, all the terms on the left-hand side of the equation cancel out. You can still use the method of undetermined coefficients in this case, but we have to alter our guess by multiplying it by x. Using the new guess, we have this yp is equal to ax e to the power of minus 2x. We have this. Oh, this is complicated. Solve the complementary equation, write down the general solution based on the form of Rx, make an initial guess. Check whether any term in the guess for yp is a solution to the complementary equation. If so, multiply the guess by x. Repeat this step until there are no more terms in yp that solve the complementary equation. Substitute yp into the differential equation and equate like terms to find values for the unknown coefficient yp. Add the general solution to the complementary equation and the particular solution you just found to obtain the general solution to the non-homogeneous equation. This is going to be difficult. I mean, if someone is watching this, how was differential equation for them? Example 7.14. A. Um. Okay, let's see. So we have 9y 0 over here minus 6 cos bx. Let's do this in blue. No. So this is the complementary equation. Minus b plus minus b square minus 4ac, but these two cancel out, so I'm just left with 9 because there's no minus 4ac. Over 2 times a. So 9 minus 9 is 0. So either the solution is 0 or it is 8 or it is 9. But then we have yx is equal to c1, just c1 because it's e to the power of 0, and then c2 e to the power of 9x. e to the power of 9x. And now the general solution. The general solution yp, a particular solution may have the form uh, a cos bx. The derivative is a sine bx. The double derivative is no, I have to, well, I forgot the inside. Yeah. So minus a b squared cos the derivative of the outside and the derivative of the inside. Now what? Now, if we put this particular solution back into the equation, we have minus a b squared cos bx. This will become positive 9. And then we have, but the thing is yp is 0. Yp, or is it? Did I get this wrong? Oh, I'm treating this as a wait, I got the entire thing wrong. Got this thing wrong. Plus 0 y. This is wrong. So yp is this, the double derivative. Okay. Wait, lambda square lambda minus 9 is 0. So let's try to solve this. The complementary equation is and then we have 0 square minus 4 times a times c. 4 times a minus 4 times a times c over 2 plus and minus 6. So plus and minus 3 over 2. Sorry, plus and minus 3. So 3 and minus 3. Right. Wait, I just have to go somewhere and then I'll come back. I'll be back in a few minutes. Hello. Hold on. Ding my mic. Sorry, I was gone for I just had to do something. So anyways, this is the solution for the complementary equation. This is a particular solution for the main equation we are finding. Now we want yp derivative, double derivative. Now we want to substitute this into that. Yeah. So we have minus, and then we have 0, and then we have minus 9 a cos b x. This is not 3x, this is bx. This gives minus 6 cos 3x. So it makes sense to let b equal 3. Yeah. b 3b 9 3 3. And then we have 9a. So this appears 2 times and becomes minus 18 a cos 3x is equal to, I can remove the minus, 6 is equal to 18a, which implies that a is equal to 1 over 3. Is that right? And then we have substitute in this here. We have a particular equation and then C1 e to the power of 3x plus C2 e to the power of minus 3x plus cos x over 3. So just for a alone, it's true. So it works. Question B. X double derivative of x plus 2 derivative of x plus x equal 4 e to the power of minus t. So seems correct. Now let's try the solution first. Whoops. Minus 4ac. But that's just 0. Divided by 2, and that's 1. So the solution is e, so x, C1e plus a the power of t plus, I think it's this, right? Hold on, let me check the thing. The last chapter. I can't. So, anyways, before I check that, the particular solution would be of the form A E uh, minus t, right? Just want to check their summary. And the derivative of this, it's not y, I keep forgetting. X, derivative of x with respect to t minus a. This remains the same. Oh yeah, and there's a C2 over there. Um, so we have this. You substitute this back into the original equation. So we have this plus, actually minus 2 a plus a gives you 4e to the power of minus t. This plus this is positive 2. This plus 2 minus 2 is 0. 0 is equal to 4e to the power of minus t. And then we have an issue. So what do we do in such a case? Okay, let's try some other equation. T times, and how did they derive it? They do, okay, they did what I think they did. A T. So first, let's take A out. First derivative T. So we have okay, derivative of the first, which is just T times the second. Less the first times derivative of the second. First times the derivative of the second. Derivative of this is minus A and then this entire thing. This thing is like this, right? So I just copy this entire thing. This minus this minus 2 plus t. Um, so substituting that in, minus t 2, and then we have 2 times this, so plus 2 times e to the power of minus t minus 2t a e minus t. Oops. Plus, plus 80, which is 4e minus t. Now what? I think instead of, never mind. Actually, yeah, I might. Instead of this, we type this. And then this. So, hold on. This plus this will give 280 to the power of minus t, and then it cancels out with this over here. But this and this also cancel out, so we have made no progress. Okay, let me see what the issue is. Derivative of the first times the second. That's the first times the derivative of the second. This is just this. Minus derivative of the first times the second. The first times the derivative of the second. So we have this and this minus 2, okay, plus this. Did I make a mistake somewhere? So this remains, and then plus 2. Uh, okay, I have to look at the solution. Based on the form, our initial guess for the particular solution is this. Well, we see that this guess solves the complementary equation, so it must be so we must multiply by t, which gives a new guess, a t e to the power of minus t. Checking this new guess, we see that 2 solves the complementary equation, so we must multiply by t again, which gives this. Okay, so if it solves the complementary equation, check whether any term in the guess for yp is a solution to the complementary equation. So my guesses for yp cannot solve the complementary equation. If it does, then I have to make another guess. So instead of 80, I now have to guess 80 square. So derivative of the first times the second. 2t a e minus derivative of the first times the second plus the first times the derivative of the second. We are left with this. And now Okay, hold on. I think it's easier if I do this. So derivative of the first times the second plus the first times the derivative of the second, which is 2 minus 2t. Wait a minute. I can extract this out. So this minus this. Like that, right? 2 minus 2t. I can take a to the power of e minus t separate. So I'm left with this minus this, right? Minus 2t. 2 minus 4t plus t square gives me imagine I do all that and the answer is wrong. Well, let's just skip this. Double derivative 2a, let's see. So 2a e to the power of minus t minus 4t and 8t square. Minus 4t and 8t square. Now we have to substitute that in back to here. Square plus 2 times all of plus 2 times that, right? So I will 4 and minus 2. And then plus x. So plus x plus x. So a times 8 to the power of minus t. Let's take this out. We took this out. This plus this plus this plus t square. So this plus this plus t square. Now t square will cancel out with minus 2t square. T and t will cancel out. we are left with 2. Is that right? 2, 2a e minus t gives you 4e minus t implies that a is 2. Did that solve? A is 2. Yes. Yes. Sometimes Rx is another combination of polynomials, exponentials, and sine, of course, or sines or cosines. And this is the case. The method of undetermined coefficients does not work, and we have to use another approach to find a particular solution to the differential equation. We use an approach called the method of variation of parameters. To simplify our calculation a little, we are going to divide the differential equation through by a, so we have a leading coefficient of 1. Then the differential equation has the form double derivative of y plus p divided by y plus p qy is equal to rx, where p and q are constants. If the general solution to the complementary equation is given by c1y1 plus c2y2, you're going to look for a particular solution of the form yp is ux plus vxy2. In this case, we use two linearly independent solutions to the complementary equation to form our particular solution. However, we are assuming the coefficient are the functions of x rather than constants. We want to find functions u and v such that vp satisfies the differential equation. We have vp is this, derivative of vp is this, double derivative is this. Substituting into the differential equation, we obtain this. And note that y1 and y2 are solutions to the complementary equation, so the first two terms are 0. Thus, we have, why are the first two terms 0? Hold on. First two terms are 0. So they mean this and this because y1 and y2 are solution to complementary. Okay. Oh, I see, I see. So if their solution to complementary equation, substituting in y1 gives 0, substituting in y2 gives 0. So we are left with this. Derivative of u y1 plus derivative of y2, derivative of that, plus p derivative of u y1 plus v derivative of v y2 plus, okay, if we simplify this equation by imposing our additional condition, this plus this is equal to, oh yeah. Wait, what? A complementary equation. So one condition is this. The second condition is that this has to be 0. First two terms are 0. And this reduces to this. So with this additional condition, we have the system of two equations and two unknowns. Okay. Solving this system gives us derivative of u and derivative of y. We can integrate to find u and y. This is a particular solution to the differential equation. Solving the system of equation is sometimes challenging, so let's take the opportunity to review Cramer's rule, which allows us to solve the system of equations using determinants. The system of equation a1z1 plus b1z2 is r1, a2z1 plus b2z2 is r2, has a unique solution if and only if the determinants of the coefficients is not 0. In this case, the solution is given by z1 is this, z2 is this. So we want to find this. Z1, Z2, Z1, Z2. R1 B1 R2 B2 A1 B1 A1 B2 A1 R1 A2 R2 A1 B1 A2 B2. Okay, this is like even more confusing. So many rules to remember. Example 7.15. X square Z1 plus 2x Z2. This correct? No, this is 2x. So Z1 is equal to R1 B1 R2 B2 divided by A1 B1 A2 B2. And then Z2 is equal to A1 R1 A2 R2 divided by A1 B1 A2 B2. So let's see. So Z1 is equal to R1 B1 R1 times B2 R1 B2. So A is over here and B is over here, right? R1, hold on. A1 B1 R1 A2 B2 R2. A1 B1 R1 A2 B2 R2. So R1 times B2, which is 0, minus R2 times B1, which is 4x squared. Now A1 B2, A1 B2 minus 3x to the power of 4 minus it with these two. So A2 B1, which is just 2x. So the numerator of this A1 R2 2x cube A2 R1 is just 0. So Z is equal to, I remove 1x, I remove 1x from here. Um, we have missed something. This minus this. So the R1 B2 and then minus R2 B1 R2 B1 minus yeah minus this is plus. Similarly, I can have a plus over here. Solve the complementary equation and write down the general solution. Use Cramer's rule or another substitute technique to find functions derivative of u, derivative of v, satisfying this. Integrate u and v to find u and v. Then Vp is this is a particular solution to the equation. Add the general solution to the complementary equation and the particular solution found in step 3 to obtain the general solution to the non-homogeneous equation. Yeah, I will just do one exercise because this will take time. So we have this equation. Find the general solution to the following differential equation. Oh, okay. So first we find the complementary solution, right? So the complementary solution. Lambda square minus 2 lambda plus 1, 0. Um, minus p plus minus p square minus 4ac, which is just 0. We are left with this, but minus p. Okay, right. So then y is c1 e to the power of x plus c2 x e to the power of x. And then they want us to solve the complement the system of equations. What do you call this? The derivative of u y1 plus derivative of y2 x is equal to 0. And we have this, and et to the wait, it's t, it's not x. I'm writing x over here. Let's just write x here. Right now we need to solve this thing. So we do a okay. Think I know how to do it. So y1 r wait, derivative y and derivative of the first times the second plus the first times the derivative of the second. This is going to take so long. Let's try. Okay, let's try to find the denominator separately. Let's call it d denominator. So this the a1 b1 so this times this, so which is e x this times this minus this times this. This times this. Y2 times derivative. Now this is equal to, let's simplify, getting e x out. So I have y and x, and then this is minus x e to x. But then this, the e to x plus x times e to x minus x e to x, they will cancel each other out. So now e to x, e to the power of 2x, right? That is the denominator. Y1 times this, y1 times this, and then the derivative of y1 times 0. And u, derivative of u and v are what we finding. This times this. So this is e to the power of x times this. So e to x, x square, 1 over x square. Now for v, we have r1, y2, and then r2, v2. Is that right? I think that's right. This, which is 0, minus y2, which is, oh my god. Okay, let's take e to the power of x out and then multiply it with this. So it becomes e to x, 1 plus x square, and then divide this by this. So all this is divided by this. Minus 1 plus x, this. And now we have to integrate them. Do we add the plus c? So the derivative of of uh, of e minus 3, so whoops, e to the power of minus 3x with respect to x. So minus 1 over negative 3 is a constant. This will become minus 3 forward, and this will become minus 2. Minus 2. No, I don't want this. I actually do want x. X, and then x minus 2, which is equal to u derivative of ux. And then if I differentiate, if I differentiate, um, if I differentiate, uh, minus, okay, x minus 3 divided by 3 plus x what I get is x negative x minus 2, the 3 and 3 cancel, and then negative x minus 1, the 2. Yeah, yeah. This is the derivative of v. So the original u is this, the original v is this. So I can substitute that in here and get the particular solution. And that's the particular solution. Let's see if that's what they got. But they wrote t. Was it 1 over x or 1 over x square? Uh, no, it's x square. Ptx. T square over here. Why did this t square? So, so did I have the part, the denominator is right? The top part, hold on. What is Z1 and Z2? R comes first and then B. Okay, R1, B1. Okay, when I am finding Z1, so integral of U, I do R1, B1, R1, B1, R2, B. Oh my God. Okay, let's try that then. I thought I would be done with this exercise. R1, B1. Hold up. R1. Okay. I need to write it in terms of, so 0, this, and then e to the power of x over 2x. Or what? X square. We need to substitute this in. E x square. This x. This, and then e to x. ex will make e2x, but this will cancel out with this. And x square will cancel out. Now derivative of v is, this time the result, no, yeah, the result is at back and the first coefficient is in the front. So y1 and 0. Derivative of y1 and then this. X to x squared. One over x squared. So now let's say derivative is x minus 3, negative 3. I will end up with x minus 2, which is what the derivative of v is. But I'm supposed to forget the plus c, right? The plus c doesn't matter, maybe. And then we have 1 over x, which is ln of x. Derivative of ln of x is equal to 1 over x, which is u. Substitute that in to this to get the particular solution. So we need to substitute these. Now, is this correct? Hold on a minute. Minus 1. Am I getting confused or something? Yeah, derivative of minus ln of t is this. Hold on. They end up with 1 over x squared. Why negative here? Why is it negative? Oh, yes, yes, yes. Oh, no, wait, no, no, no. What do they get? If this is correct, how did they end up with minus 1? This minus the, okay, yeah, minus. This minus this, so 1 over x squared. Now, a derivative of ln of t gives 1 over t, which I understand. Now, derivative of minus 1 over t. Derivative of, I see what I did. I did a mistake. Minus 1 goes here. Minus 1 goes here. Cancels out with this, and this becomes minus. Subtract 1 from this, and we get minus 2. Yes, yes. So it's minus 1 over x. Minus 1 over x. And then that's the particular solution. particular solution is we don't have a plus C here. We substitute that in, and then e the term e to the power of t, this term, or there's already a term here which is e to the power of t. So we can make a new coefficient out of that. So we don't need to. Okay, understand. So okay, what's the next chapter? The next chapter, I will do it in the next stream. It's about applications and series solutions to differential equations. How long is this? Application. Okay, I'm going to rush through this topic because like right now I'm not concerned about applications. So that's when I will do physics and series solutions. Okay, I'll end the stream here. And next stream maybe my last calculus reading stream. I will still be doing calculus from different books, but it will be my last calculus stream with OpenStax. Yeah. So it's like almost like 55 videos. I will end the stream here and I will see you guys next time. Bye.